The Antarctic ice sheet has existed for many thousands of years. So too the Greenland Ice Sheet. And also the sea ice in the Arctic Ocean off Greenland. But these ice sheets are not permanent features of the planet Earth. If we take a look at the history of the Earth going back 2.4 billion years, ice sheets and ice ages have existed for only about 27.5% of the total time. Focusing on the last 260 million years, ice sheets have existed for only 1% of that time, and that is for the most recent 2.6 million years, the period known as the Quaternary Ice Age. Prior to this ice age, for nearly 260 million years, there were no extended ice sheets on the planet. So what caused them to form and for the Quaternary Ice Age to begin? Attempting to answer this question will help us also understand many of the mechanisms underlying modern climate change. The theory of the Milankovitch cycles had not been widely accepted until studies carried out in the 1970s. This study by Hayes, Imbrie and Shackleton is widely cited by climate scientists. The paper concluded that the Milankovitch cycles are the fundamental cause of the succession of Quaternary ice ages, but not the only cause. This overall conclusion was largely adopted by the IPCC. Later studies agreed that the Milankovitch cycles were a fundamental and necessary condition, but they were not a sufficient condition, and that some set of positive feedback factors must be also involved. So the condensed answer to our question is that the Milankovitch cycles, plus other factors, caused the start of the ice ages. But what are the other factors, and how do they interact with each other? The set of factors influencing the climate is large, but this list would constitute a major subset. We should also bear in mind this statement from a recent study. It points out that to understand the climate of any particular time, we must take into account the historical events leading up to that time. We will adopt this approach and follow how the Milankovitch cycles combine with the other factors over millions of years to bring about the Quaternary Ice Age. We start 210 million years ago. At this time, the Earth's continents formed one large supercontinent, Pangaea. However, from around 175 million years ago, the supercontinent began a long process of separation as a result of the movement of the Earth's tectonic plates. According to the tectonic plate theory, the Earth is made up of a collection of large plates that are constantly moving, albeit slowly, at a few centimeters per year. The movement of the plates resulted in the separation of the continents. But this movement also produced other impacts, such as earthquakes and volcanoes. Volcanoes can have an almost immediate effect on the climate, but they can also produce longer-term impacts, especially as a result of a series of eruptions. Such a series took place in what is now the Deccan volcanic province in India. The Deccan traps erupted in a series of 3 phases, centering around 65 million years ago. It was one of the largest volcanic eruptions in the history of the Earth. Hand in hand with the separation of the continents, the oceans were also fundamentally changed. When taken alone, this would have had an enormous effect on the climate. It is difficult to overstate the complexity of the ocean's influence on the climate. These are just a few of the ocean currents that interplay with each other. To pick out the global ocean conveyor belt as an example, it transports cold bottom water from the North Atlantic to the south of the equator, all the way down to Antarctica. From here, the waters bring cold temperatures into the Pacific. But the journey into the Pacific gradually warms the water so that it becomes less dense, resulting in the cold bottom waters rising to the surface and passing through the Indian Ocean as a warm stream that continues onto the Norwegian Sea. It takes almost 1,000 years for the conveyor belt to complete one full oscillation. Throughout the breakup of Pangaea, the Sun would of course have been a significant other factor. And any changes in the Sun's output would have driven changes to the climate. But while the Sun has its own cycle, which has a periodicity of around 11 years, that a recent study indicates could well have been in effect during this period, there does not seem to have been any unusual behaviour prior to the start of the ice ages. The behaviour of all greenhouse gases during this period is difficult to determine. However, carbon dioxide levels have been estimated. This chart goes back more than 500 million years. It shows the ratio of the mass of carbon dioxide in the atmosphere compared to that existing at present. If we look at the Karoo Ice Age, roughly 260 to 360 million years ago, we can see a marked reduction in carbon dioxide levels. While during the start of the 260 million year warm period, levels rise before beginning a steady decline. At about 55 million years ago, which is the approximate start of the Eocene epoch, the planet Earth had been fundamentally changed. The separation of Pangaea was coming to the point where the continents were forming into the structure we know today. Violent volcano eruptions had taken place. New oceans and ocean currents had formed, while carbon dioxide levels had fallen. But nevertheless, the Earth still had no extended ice sheets. To appreciate the next steps on the way to the inception of the ice ages, we need to more fully understand how the Milankovitch cycles work. As explained by the IPCC, the theory proposes that when there are periods of low insolation at 65 degrees north, then this triggers winter snowfall to persist and accumulate to form northern hemisphere ice sheets. Latitude 65 degrees north coincides approximately with the tip of Greenland. A study published in 2016 provides more detail of how this mechanism works. This study emphasizes the importance of when extreme points of the Milankovitch cycles coincide, or, as the paper puts it, when they are in phase. The paper refers to this condition when a combination of obliquity and precession places the Earth's tilt at its closest to the perpendicular, and eccentricity has the Earth at its closest to the Sun. The Milankovitch cycles are thus in phase to produce warmer conditions that would not encourage winter snowfall to persist. However, as the Milankovitch cycles go through their phases and the Earth's tilt moves further from the perpendicular and eccentricity moves the Earth to its furthest point from the Sun, then the cycles are in phase to produce low insulation, which would then encourage winter snowfalls to persist and hence accumulate to build the Northern Hemisphere ice sheet. The combined effects of the Milankovitch in phases and the cooling effects of the other factors gradually, after one warming phase, took the Earth into a long cooling trend. The trend continued through the end of the Eocene at around 34 million years ago, and at this juncture cycles of colder and warmer periods can be detected, so that the Antarctic ice sheet expanded during cooler periods and contracted during warmer cycles. The cycles continued up to the start of the Pliocene epoch, at which point the climate had become cooler, drier, and more seasonal. But a Northern Hemisphere ice sheet was still to form for any length of time, while the Antarctic ice sheet continued to fluctuate in size. This juncture also marks the time where the influence of the Milankovitch cycles becomes pronounced. This chart shows cycles of warmer and colder periods occurring with a periodicity of around 41,000 years, which corresponds to the Milankovitch obliquity cycle. The obliquity cycles continued to drive down the global average temperature over the next 2 million years until we reach the mid-Pliocene. Then the Greenland Ice Sheet started to evolve, although the Antarctic Ice Sheet still continued to fluctuate. Atmospheric carbon dioxide concentrations had reduced to between 360 and 400 parts per million. However, global mean temperatures were still around 2 to 3 degrees centigrade higher than pre-industrial levels, and the sea level was between 15 and 25 meters above modern levels. Over the next 700,000 years, the cycles continued, but still no long-lasting ice sheets developed. However, around 2.6 million years ago, the feedback between the other factors and the Milankovitch cycles amplified the effects of each other, so that a breakpoint was reached. From this point forwards, the Greenland and Antarctic ice sheets expanded, and a spiral of feedback and accelerating events is set in motion. The increased volume of ice not only disrupts the ocean's conveyor belt, but also captures carbon dioxide and other greenhouse gases, which decreases their concentration in the atmosphere, which in turn caused further cooling and more ice to form. And so the cooling cycle accelerates and accentuates one more climate change factor. This is the albedo effect, which is where the Earth normally reflects some of the sun's irradiance back into space. But snow and ice reflect more than do land and sea. So an increased surface area of snow and ice in the Greenland and Antarctic ice sheets resulted in a greater reflection of solar energy, and thus a reduction in the total solar irradiance absorbed by the Earth, which added a further cooling effect to those of the other factors. And as a result, the Earth's climate spiraled down and finally entered the Quaternary Ice Age. The effect on the world was profound, for it was at this point, for the first time in 260 million years, did distinct climate periods occur that alternated between times of cold glaciation and warmer periods with little or no northern hemisphere ice sheet. We currently live in such a warm period, the Holocene interglacial. And the fundamental cause of this? The IPCC confirms the findings of earlier studies under the heading of orbital forcing, and identifies the Milankovitch cycles of eccentricity, precession, and obliquity as being the pacemaker of the transitions between glacials and interglacials. So thanks to the Milankovitch cycles, and of course all the other factors, we now live in a time of glaciers, with an ice sheet on Greenland and an ice sheet on the Antarctic.